The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Alright, so I'm going to work through problem 12 for Physics 2020 Midterm Exam 2, year 2006. And this problem says, find the tension in two ropes shown in figure chandelier. And I guess they're referring to this supplemental sheet that they gave on to the exam, with the exam, that has all the figures on it. And so basically we're looking at this top left figure, which is the figure chandelier. And I have re-represented that figure here. I've illustrated it here. My crude drawings. Don't make fun of me. I know I can't draw. But basically I did the best I could. And so basically what you have is you have a chandelier that's being held, that's attached to a rope, which is attached to two ropes that are attached to basically some structure, probably a wall and a ceiling. And so the weight of this chandelier is basically acting down, and it's causing tension on, it's a tension force on these two ropes. And we're asked to determine basically the tension in these two ropes caused by the weight force from the chandelier. And it says we're going to, for the response, we're going to list F1 is listed first, and then we're going to list F2. So in order to solve this problem, you got to do a couple of things first. First, we need to define our coordinate system. Okay, that's the first thing you're generally going to do in physics, is you're going to define your coordinate system. So we'll define our positive y in x direction to be like this. Okay. The next thing we want to do is a free body diagram. Okay, so basically a free body diagram, all we were going to do is we're going to draw basically a dot that represents our free body, and we're going to draw all the forces that are acting on this free body, and we're going to draw them in such a way that they correlate to our coordinate system. Alright, so we've got three forces here. So let's start with the chandelier force. So basically this is just a weight force, and we know that that's acting in the negative y direction based on our coordinate system. So we can draw this force in this way. We'll call that weight force Fw, and from the illustration in our diagram, we know that's 600 newtons, so we know that that's 600 newtons. We also have a tension force, which we're going to call force 1, that's acting in this direction. So if we say that this is our x and this is our y, okay, we have a force 1 that's acting basically like this, and we know that this angle here is 45 degrees. Okay, so this angle here is 45 degrees. And we also have another force that's acting in this direction. We'll call that the second tension force, we'll call that F2. And so basically we have our free body diagram. Okay? Now, that's the first step. The next step is understanding that from Newton's law, that the sum of the forces is always going to equal to the rate at which it's going to accelerate, or mass times acceleration. Okay? So we know that the sum of the forces are always going to equal to ma. Now, the important thing to know here is that if the object is not moving, then we know that it has no acceleration. And if it has no acceleration, then this part of the equation has to equal to 0, because if A is equal to 0, this whole thing is equal to 0. So in our case, the chandelier is being held up, so it's not moving. So we know that it's stationary, so it has no acceleration. So this right-hand side of the equation is equal to 0. Another thing we need to know is that since the total forces, the sum of the total forces is equal to 0, and it has no acceleration, that means it has no acceleration in the A or the Y direction. So we know that the sum of the forces in the Y direction has to equal to 0 in this case. And the sum of the forces in the X direction also has to equal to 0 in this case, because acceleration is 0. Okay, so if we can basically resolve all of our forces in our free body diagram into their components, in our X and Y components, we can sum up the sum of the forces in the Y and in the X direction, set that equal to 0, and see if we can solve for the missing components. So if we do that, then we resolve this force 1, okay, into its X and Y components. We get a, let's basically use a different color here. We get, let's call this force 1y, okay, and we resolve the X component, so we'll call that force 1x. Okay, so now instead of the force 1, we're going to use the components of force 1 in the Y and the X direction. And if we do the same thing for F2, well, we know that F2, there is no Y component, it's just acting in the X direction. So this is the force, so then the force 2 in the X direction is equal to the total force of the second tension force. And we know that the weight force is only acting in the Y direction, the negative Y direction. So the force of the weight in the Y direction is equal to the total force, right? Because there is no X component, and in here there is no Y component. All right, so if we sum the forces in the Y direction, we have F1Y, okay? So in order to determine F1Y, we need to basically use our knowledge of trigonometry, because they gave us some additional information about the angle between this force and basically the ceiling. They said is 45 degrees, so that theta is 45 degrees. And so we know a relationship between, if we have this as theta, okay, this is opposite of theta, so this is the opposite, and we know that this is force 1 is the hypotenuse, okay? So we know that the sine of theta is equal to the opposite over the hypotenuse, okay? But the opposite in this case of theta is force 1y, so that's force 1y. And the hypotenuse of this right triangle, okay, we're talking about this right triangle here, okay, of this right triangle is force 1. So now we have a relationship between theta and force 1 and force 1 and the y component of force 1. If we solve this equation for F1y, we get F1y is equal to the force, the magnitude of force 1 times the sine of theta. Okay? So that's our first force acting in the y direction. We have another force that's acting in the negative x direction, which is the weight force. So we know that the weight force is equal to 600 newtons. Okay? Now all we have to do is sum these forces and set those equal to 0. So basically, F1y plus 600, actually, we know that the the force is minus 600 newtons because it's acting in the negative x direction. So I guess the best way to do it so you don't get confused, okay, we'll just put the magnitude, which is 600. So F1y plus Fw is equal to 0. Okay, so when we substitute this in now, F1y is basically F1 times the sine of theta plus Fw, but Fw is minus 600, so that's minus 600 because it's acting in a negative direction, okay, is equal to 0. Now, what we can do is we can solve this equation for F1. We can say that F1 is equal to 600 newtons, taking the 600 to the other side, and divide that by the sine of theta. And so F1 is equal to 600 newtons divided by the sine of 45 degrees. And when we plug this into the calculator, we get approximately 848 newtons. Okay? So this is what F1 is. Now, we can do the same, we can now find the all the x component, all the forces acting in the x direction, and we can sum those. So what do we have acting in the x direction? We have force 2, so basically the first one we have, which is the second tension force, and we have we don't know what that is, okay, and we also have basically the x component of force 1. All right, so we have those two forces. Okay, but can we find the x component of force 1? Well, we'll do something similar. We know that the x component of force 1 now has to do with instead of the opposite now, it's this force, so which is the same thing as this one. So that's basically adjacent to theta, which is the theta in our right angle. And so we know that the trigonometric function that relates adjacent on the hypotenuse in a right triangle is the cosine. So we know that the cosine of theta is equal to adjacent over the hypotenuse. In this particular case, it's F1, the x component of F1, over F1. And if we solve this equation for F1, well, if we solve this equation for F1x, we get F1 times the cosine of theta. All right. Now all we need to do, so this is basically, if we sum the forces now, we get F2 is acting in the positive direction, so we get F2, and we have F1, the x component, is actually acting in the negative direction, so F2 minus F1x is equal to 0. Okay? And in this case, we can take F1x to the other side. So we know that F2 is equal to F1x. But F1x is equal to F1 times the cosine of theta. And we got that relationship here. And so we know that F2 is equal to F1. We know that F1 is 848 newtons. We just found that. Times the cosine of 45 degrees. Okay? So now we just put that into our calculator, and it works out to be around 600 newtons. So basically, we go back to our problem. It says that we should list F1 first and then F2 for our answer. And so we get 848 newtons for F1, and we get 600 newtons for F2. So this is F1 and this is F2. And we look at the potential solutions, and we see an 845. Okay, so remember, they're listing them in order, so the first number that you see in the solution is F1. So if we look at all of them, we have 600, so that's not right, 845, well that's close, but if you look at the second, the F2, it's another 845, so that can't be right. And so none of the solutions are right, except for, so we choose number 1, which just says none of the choices are correct. Okay, so the solution is basically no correct choices. Okay? So, let's just kind of review what we did. We had a forces that was acting on this chandelier to kind of keep it stationary, and the weight of the chandelier was causing tension on the ropes, so we drew a free body diagram acting on our chandelier, and from the coordinate system that we defined, we were able to resolve all of our forces into their x and y components, which is something that you should usually do whenever you're working with these types of problems, resolving your forces into their x, y components, because you know that the sum of the forces is equal to MA, and that means the sum of the forces in the y direction and in the x direction also has to equal to MA. In this particular case, there was no acceleration because the chandelier was stationary, so we know that the MA term on the right hand side of the equation goes to 0. That made the rest of the problem fairly simple once we resolved our forces. We used trigonometric functions and basically the information given in the problem in order to relate the magnitude of force 1 into its x and y components. And so then we just sum the forces in the y direction, sum the forces in the x direction, and we were able to find the solution. So this is your general approach to solving these types of problems.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.